On this page of our notes, we are going to look at how to graph a logarithm. On the previous page, we started with an exponential and obtained the logarithmic graph by just doing the inverse. On this page, we're going to do the opposite. We're going to start with the logarithmic function and graph its inverse and get the exponential. Here's our standard form for a logarithmic function. It has an hk in the same way that our exponential did. As we saw on the previous page, logarithmic graphs have vertical asymptotes, but the vertical asymptote will pass through its hk. Just like with the exponential, this hk will not actually be on the curve. The inverse of my logarithmic graph will be an exponential, and it will be a reflection over the line y equals x, just like we saw on the previous page and at the beginning of the chapter. We'll find it by reversing the points again, simply switching the x and the y. In order to create our smart t-chart for our logarithmic graph, we will need to remember two very important log rules, that the log of 1 is always 0 and log base b of b will always be 1. This is going to help us make our very quick and easy t-chart. So as I jump into this logarithmic graph, the first thing that I'm going to do is I'm going to identify my h and k. When I'm looking for the h value here, I'm mentally setting this argument equal to 0. I'm trying to figure out what value will make the argument 0, and in this case it's 5. My k value is a -2. So just like we saw on the previous page, we can immediately plot that point, and since it's a logarithmic graph, I can put its vertical asymptote in immediately. I can always jump right in and calculate the x and the y-intercept. So if I let x equal 0, I can go ahead and I can just plug in to my function and get y equals log base 3 of 5 minus 2. Sometimes in this form, students are tempted to combine that 5 and that -2. You can avoid that error by putting the -2 in the front. And then there's not as much temptation to do that. If we want to find our x-intercept, we're going to let y equal 0. Finding the x and y-intercepts gives us an opportunity to practice our solving log and exponential equations. 5 minus x minus 2. Going to move my 2 to the other side. Switch to my exponential form, so I'll have 3 to the second power, which I can just do in my head as 9. Continue solving. I'm going to move my x to the left and my 9 to the right, so I get x equals -4. I'll write those as ordered pairs when I get to the bottom of the page and summarize everything. Next, I'm going to move on to my smart t-chart. Just like we saw on the exponential page, it's easier to start on the right-hand side and think about what we want to happen. So thinking of my log rules from up above, I would like to be able to do log base 3 of 1 minus 2, because I know that log base 3 of 1 is simply 0. So I would get a nice -2. I would like to be able to do log base 3 of 3 minus 2. You can put parentheses around that. I know that log base 3 of 3 is 1, and 1 minus -2 is -1. So now that I have the right-hand side, I just need to go back to the left-hand side and figure out what x values would create these appropriate arguments. So the actual argument for my log is a 5 minus x. I want the argument for the log to be 1. Solving that little mini equation, I get a nice 4. And now I get this nice ordered pair. Again, my argument for my log is actually 5 minus x. I want it to be 3. 3 is the base of the log, so that's what I'm focusing on. Moving my x to the right and the 3 to the left, I get a 2. So now I have, again, another nice ordered pair. You'll notice on this particular problem, this doesn't always happen, but you'll notice on this particular problem that my x-intercept is actually a really nice number. So I could include that in my graph if I would like. So I'm going to plot my points for -2. Again, closely aligned with that HK, and that should always happen, to -1. And if I want to even go ahead and graph this x-intercept at -4, I can do that. Now, I'm definitely not tempted to create this as a line, but thinking about my logarithmic graph, it needs to come down and approach the asymptote, and needs to come up and start to flatten out. Nice arrows on the end. Of course, I can find its inverse now very easily, remembering that the inverse of this function will be an exponential. My asymptote, instead of x equals 5, it's going to become y equals 5. My HK was originally 5, -2, so now my new HK is going to be -2, +5. I can take my t chart that I did from up above, and I can go ahead and just reverse that. So instead of 4, -2, I have -2, 4. Instead of 2, -1, I have -1, 2. These are the new points I'll plot. So I have -2 up 4. I have -1 up 2. And again, if I wanted to reverse this other point, my x-intercept, it will become my y-intercept. So I could plot that one as well. You'll notice that this inverse looks different than this exponential looks very different than the exponential that we had on the previous page, because this one has been reflected. So although these graphs look very strange when we put them on our grid, we can see that when we draw in our line, our identity line of y equals x, the graphs are still reflections over it. So now all that we need to do is go ahead and summarize our information about our graphs on the bottom. Thinking about our logarithmic graph first, that was all in the blue. My asymptote was x equals 5. My y-intercept, we calculated it up above, is 0. I'm going to go ahead and write it as the -2 in front, plus log base 3 of 5. Remember, we can do it either way. The x-intercept we saw was that very nice x-intercept. My domain for a logarithm always is going to have a restriction, and I can see it algebraically from up above using this argument of 5 minus x. Graphically, I can see that it's only to the left. So it's -infinity to 5, not inclusive. My range, of course, is all real numbers. And for the inverse, I'm just going to flip everything exactly like we did before. The asymptote becomes y equals 5. The y-intercept comes from my x-intercept. My x-intercept comes from my original y. My domain comes from the original range. My range comes from my original domain. And we should be able to look up above and see that these actually make sense. And that's everything that we need to know related to our graphing logarithms and their inverse.